Inferential statistics pertain to taking a small sample of the population and then using that sample to estimate the characteristics of the larger population from which the sample has been drawn. One specific statistical test you can use to make inferences about a population is analysis of variance, or ANOVA. ANOVA is used when you have a question about whether 3 or more groups are different. Suppose, for example, our organization has instituted a new customer service training for its employees. We believe that newer employees who have been at the organization 2 years or less are eager to learn and improve and will probably demonstrate great customer service after the training. We also believe, however, that employees who have been with the organization for 3 to 9 years are somewhat less eager and will probably demonstrate a little bit weaker customer service after the training. And finally, we find that employees who have been with our particular organization 10 years or more are kind of cynical. We believe they probably won't pay much attention to the training at all. Thus, after the training, their customer service will probably be the lowest. So we're interested in 3 groups: employees who have been with the organization 2 years or less, 3 to 9 years, and 10 years or more. We now have a research hypothesis, which might be stated: after customer service training, time with the organization affects customer satisfaction ratings such that as an employee's organizational tenure increases, his or her customer satisfaction ratings decrease. Let's suppose that after a randomly chosen training session, to which employees were randomly assigned, the group of newer employees receives an overall mean customer satisfaction score of 4.8 out of 5. The mid-tenure employees, 3 to 9 years, receive a 4.5. And the long tenure employees, more than 10 years, receive a 4.1. On the face of it, these values seem to support our hypothesis. 4.8 is greater than 4.5, and both of these are greater than 4.1. However, as you may recall from our learning resources on hypothesis testing, the default null hypothesis says that there is in actuality no true difference between the groups. The null hypothesis states that the difference we have observed is simply error, or an artifact that's been created by our sampling methods. The null hypothesis suggests that if we ran the test again and again after all the training sessions for the entire population, we would probably not observe any difference between the groups. Therefore, we must conduct a statistical test, analysis of variance, to determine if we can reject the null hypothesis and accept our proposed alternative hypothesis that our observed differences are reflecting a real difference in the population, that our observations are not simply sampling error. We use ANOVA to test our null hypothesis. It requires either manual or computer calculation of the value of the test statistic f, which is in turn used to determine the probability that the null hypothesis is true. We call this probability the p-value. Usually, if the probability that the null hypothesis is true is less than 5%, or p less than 0.05, then we can reject the null hypothesis and accept our alternative hypothesis that indeed the means, and therefore the groups, are different. In this case, if our calculations reveal that p is less than 0.05, we could say that after customer service training, time with the organization does affect customer satisfaction ratings, such that the longer an employee is with the organization, the lower the ratings will be. We call this a statistically significant difference between the groups. There are some very important things to keep in mind with respect to ANOVA. First, the null hypothesis that is rejected at p less than 0.05 is the hypothesis that the entire set of differences is the result of sampling error. In this example, the entire set of differences would include the differences between newer and mid-tenure employees, mid-tenure and long-tenure employees, and newer and long-tenure employees. So when we reject the null hypothesis, we know that at least one of these differences is statistically significant. But we don't know which one, nor do we know whether or not 1 or 2 or all 3 observed differences are significant. A post hoc test, that is a test that you run after you find a significant ANOVA, must be run to tease out the individual significant differences. Sheffey's test is a common post hoc test. Tukey's honestly significant differences is another. Either of these provides the probabilities of specific pairwise differences. Second, An ANOVA between only two groups will return the same result as a t-test. So why don't we just run a bunch of t-tests between and among all of our groups? Because running t-tests over and over among the groups greatly increases our risk of type 1 error, or of mistakenly rejecting a null hypothesis that is in fact true. This would result in believing in the significance of an observed effect that is actually simply the result of sampling error. This can have a negative consequence if we move forward, for example, making decisions based on incorrect information. One condition of ANOVA is that the dependent variable is measured on a continuous interval or ratio scale. Additionally, ANOVA can be used only when the following assumptions are met or nearly met. The population from which the sample is drawn is normally distributed. Each observation of the dependent variable is independent of other observations. The variances of the group are homogeneous. This last condition is known as homoscedasticity, an ungainly word that you will see in discussions of ANOVA in the literature. When you see studies comparing 3 or more independent groups in the scholarly literature, you may also encounter the non-parametric equivalent of ANOVA, the Kruskal-Wallis test. Non-parametric tests make fewer assumptions about the data than do parametric tests. So we use them when we cannot assume, for example, that the data is normally distributed or that the variance is homoscedastic, as is the case with categorical data. Overall, analysis of variance is a commonly used inferential statistic that you will need to know in order to conduct basic research. You will also see it frequently in the scholarly literature. It's important to understand why and how it is used so you can both conduct your own research and evaluate the literature appropriately.